Alright, so over about the past week, I haven't done too much with this. Polished up the notation a little bit. It's about where we stand. This is more or less what I showed last week, and here's uh, the geometry, finding areas and volumes and shit. One thing is, so all of these, we're given all of the pieces between the curly brackets, and then we're finding, so we're given a reference frame and we're applying transforms to it, commutative. If you unroll this loop that is indicated with this repeat operator right here, if you unroll this, everything in here is commutative, right? It becomes a commutative batch function. Okay. The transform over the reference frame yields this transformed reference frame B. That's the thing that we're finding. If instead we are given the transform reference frame, the initial reference frame, and the shape coefficients in the base, then the thing that we're finding is k, the number of iterations, and that means we're taking logarithms. And when we do that with respect to functions, that pretty much just gives us calculus, right? So your first, so uh, if your number of iterations is -1 and we're working over functions, then what you're doing is you're taking a derivative. If it's +1, what you're doing is you're taking an integral. If it's some larger number, positive or negative, then you're taking like a second derivative or a third derivative or a double integral or something like that, like whatever the number is. All right, so the logarithms here with respect to functions basically just give us calculus. And you can't really generalize them. If you could, we would be able to generalize closed forms for calculus, for integrals and stuff like that. I'm pretty sure we're not going to be able to do that, at least not with this limited um, uh, availability of operations. Tinkered around a little bit with shape constants for regular polygons with respect to an embedding square. So basically the reference frame, the reference shape that you're considering is a square. So its area is 1, and then all the other regular polygons up to the circle are embedded in that. And what we're doing is we're finding the relative area of the polygon compared to the square or rectangle. Like the equilateral triangle doesn't quite fit in a square. There isn't a way to get that to work, but all of the other ones do. So, yeah. And there's sort of a general approach. This n cos pi on n, sine pi on n part is the polygon, and it's actually in all of them. And then there's two pieces squared, that's the square itself. So you got the polygon relative to the square. So the polygon is contained within the square, which is what division always means. That's what per means. That's why we're using the Coptic word for house to indicate division, right? The polygon is housed within the square. That's how this shit works. It doesn't look like these equations are the same, but they're pretty much the same. Um, so this is when there's the number of sides is equally divisible by 4. Here the number of sides is even but not equally divisible by 4, and here the number of sides is odd. Here what's happening is you've got the, well, the 4 is coming from the fact that we've got cos whatever plus itself. So there's 2 of them in there, and that's getting squared, so like you can just pull 4 out of there. Here the angle is that's in the cos denominator thing is pi on n, right? So cos pi on n squared as the denominator. When you have a cos pi on n in the numerator, 1 cancels, and then you're left with a sine pi on n over cos pi on n, which is just tangent pi on n. So this is really the same exact thing, just you can shorten up the writing of it, so I chose to do that. But they're ultimately the same thing. And then looking at some shape coefficients for integrals, not an exhaustive list by any means, and a lot of it isn't even filled out, but wherever we get like yeah, a lot of them I have written in here. Yeah, so then I was also thinking that these things that are lists, right, z, x, we can just represent them with base 1 polynomials, right? So base 1 polynomial, what we're doing is each term, each element in the polynomial is being multiplied by the base to the index of the term, right? But if your base is 1, then we just get what we see. We just get the term itself, right? Because 1 to any power is just 1. So nothing terribly interesting happens. We don't get it becomes just an identity transform over the element in there. So we can just use base 1 polynomials, right? Which isn't that weird because our number system is base 10 polynomials, so this isn't weird. And if you combine base 1 polynomials, you naturally get matrices anyway. So in a sense, we're already using them for some structures that we're using. So yeah, we can store all of the x data and all of the z data into these base 1 polynomials. And there's some nice little tricks we can apply. So because it's a base 1 polynomial, we don't have to write it, so we can simplify that slightly. And then what we can do, because z0 and x0 don't actually show up in these recursive loops, we can set a to be the same as z0, and then we'll just give identity to x0, and that turns out to have some benefits. I don't actually at the moment remember what that is, but they do exist. Alright, so now your fully generalized form looks like this. So really we don't have an a anymore. It's just part of z. And k, we could kind of abstract that away. What this is just a convenience for notation. Because this part, if we could unroll this loop and they just become explicit terms, right? And they're all now commutative. We can totally do that. That's fine. That's the entire point of this notation in the first place, was to be like, well, it's not binary and it should be commutative, so let's make it a commutative batch function. Hey, look at that. So you can still do that, right? And then there's some weird consequences where B ends up being this weird triangular structure. I don't know what the hell that is. And there's other things that I haven't seen in math, like logarithms with functions as their base. The base is always constant, even though it really doesn't have to be. And when it isn't, you just get calculus. Apparently unnamed structures that are fundamental to the general form that we're using here. So the trivial cases for x and z. For z, that's just ones, a base 1 polynomial with all of the terms being 1. All of the terms being identity. That should be a 1 right there, I think. The trivial case for x, so we get some value repeated to the left forever after an initial identity term. And then classical names related to structures fundamental to the general form. Infinite series, we don't really need that concept anymore, because that's what a base 1 polynomial is. and playing with logarithms of values versus logarithms of functions. Um, yeah, so you can see, so here is a nice little demonstration of x to the 0, regardless of what x is. It's always going to be 1 because this doesn't occur. All you get is z naught. That's the only term that appears. You get no, the base never interacts with it, so it doesn't matter what the base is by definition. Okay, so in all of this, we have correctly defined exponentiation in a way that yields 0 to the 0 being 1. But also we can show that taking logarithms of functions doesn't really help us too much in like finding a general solution to calculus, right? Being able to find closed forms to all integrals, that kind of thing, because your shape coefficients can involve a division by x, which cancels out the multiplication by x, right? So sine x turning into negative cosine x, the shape coefficient that's involved is negative cotangent x divided by x, which cancels out the multiplication by x, which is inherent to the integration. So, if you graph this, this is fucking crazy looking. I recommend it. It is weird. Why that is what this is, I don't fully understand. And on some levels I do, but I don't. Right? Or like something with like e to the x, right? Your shape coefficient is just the inverse of x, because what you're doing is you're multiplying by x, and that needs to cancel because this is its own integral. It is its own derivative, right? So it doesn't matter how many terms out you go. You can't really determine how many terms out you've gone, right? How many iterations have we gone? No idea, because it looks the same. It never changes, right? So we can't really take a logarithm of this. It doesn't actually make sense. Well, it's undefined, right? You're not going to get a definite solution to that. And here, you're also not. And see, we can see that from here, where we get this repeating cycle of 4. Right, so we can tell something by where we're at in the sequence, but not much, because it's an infinitely repeating sequence. It's an infinitely repeating pattern. That's about where I got it to. Nothing groundbreaking. Mostly just a little bit of refinement in the notation, slight expansion on what we can do with it, cleaning up the underpinning philosophy, hopefully resolving a bunch of mistakes that I made in that first presentation. There were plenty. That's fine. That's how we get there. That's you make mistakes, identify them, solve them. That's how you get where you're going. If you can't do that, you're never going to get anywhere. You make mistakes and you try to cover that up and be like, "Oh no, I didn't make any mistakes." Then, you're just screwing yourself over. Honestly.